Okay, here we are. This is unit number 8 on the normal distribution. My name is Mr. Jackson.
And I'm Miss Hughes.
And here we go with lesson number 1.
All right, so today we're going to introduce you to the normal distribution, but I'd like you to think back and recall histograms, if you would. Remember that it's a continuous variable that we use to generate histograms, and we could set up intervals and then populate a frequency table and then graph all the resulting frequencies as a histogram or a polygon. And we want to look at some of the different ways that histograms can be distributed or spread out. Okay, so first of all, if you've got sort of a tail heading out towards the left and you've got your data pushed over to the right, we call that a negative skew. Okay, so that you've got this tail of low numbers that are far to the left of your median value. That's okay. Go ahead, Mr. Jackson. Flip over to the next one. We're good. We're ready to go. Or it can have a tail that slides over to the right. So you have a bunch of positive numbers that are over on the right-hand side, and your mode would be sort of shifted over to the left, and we call that a positive skew. Okay. It could also have more than one mode. Okay, so you can have bimodal or multimodal, and in this case we'd have two different modes. One thing to think about, some things that give bimodal distributions are things like shoe sizes, like men's and women's shoe sizes. There would be sort of a mode for women's sizes and a mode for men's. Same thing with heights or things like that in terms of gender. So in the social sciences, you see things like this. You see a lot of bimodal distributions. So we can have that too. But there is another kind that we can have. We can have a histogram that when you generate it, it looks sort of symmetric. That there are an equal number of values to the left of what would be the mode or the median and an equal number of values to the right. And this kind of symmetric distribution, where you've got about half the data below the mean or median and about half the data above, we call that a normal distribution because we see it so often, especially in the social sciences. It's so familiar and so useful, and we see it all the time, that it's the norm, and that other things end up being not the norm. Okay. So do you want to take us through, Mr. Jackson, explain a little bit about what is this normal distribution?
Yeah.
We can focus in on it.
So we're going to talk a little bit more about this normal distribution. And really, this right here is what you may have heard what's referred to as the bell curve. And this is a bell curve. And, very often what we hope for is that, a class will have grades that will approximate a normal distribution. We wouldn't want to see a class with, a bimodal distribution. Really, we'd want to see a nice normal distribution, hopefully with a negative skew, so that the mean was a little bit higher.
Higher, yeah. I want to see that negative skew.
So let's talk about properties of this normal distribution. Physical quantities, height. Let's say if you looked at the height of the men in our class, or the mass of the men in our class, or similarly with the women, what you'll find is that they will be distributed in general symmetrically about the mean. There's going to be some people, some of the people that are higher than the mean, above the mean, some people that are below the mean. And statisticians observe this bell curve so often that we just refer to it as normal, because this is what happens in nature very, very often. The physical sciences, social sciences, psychological sciences really make extensive use of this normal distribution. So in this unit, even though we only have 3 lessons, this is the beginning of really what most of your university course on statistics is going to be all about.
Yeah, and especially if you do anything in the biological sciences with data, it's the same thing. The weights of walruses are normally distributed.
Yes.
You'll hear that over and over again. Yeah.
So let's talk about the normal distribution and what it's all about, because there's 4 facts that make it interesting. So if a distribution is to be considered normal, then the mean equals the median equals the mode. All 3 of these statistics for the normal distribution are the same. Now, what we will tell you is that the normal distribution is hypothetical.
It's an ideal.
The perfect normal distribution is a mathematical, hypothetical, and ideal situation. Most things that we will look at in nature approximate a normal distribution and come very close to approximating. So you may have a data set where the mean, the median, and the mode are not all the same. But there are certain statistical tests that we can do that will test to see, are they close enough? And then we can say it approximates a normal distribution. So fact number 2 about the normal distribution is that 50% of the data values lie below the mean, and 50% of the data values lie above the mean. Okay, so an even distribution, you can see this reflected in this diagram. There's 50% of your values below and 50% of your values above. The normal distribution is a continuous curve. And so if you've got 50% of the values below and 50% above, then the area under the entire curve is equal to 1, or 100%. So it basically means when you've got a normal distribution, you have 100% either below or above. So someone fits in somewhere. Even an outlier way out here on this axis is still considered to be part of this normal distribution. And they would be included in this 100.
Yep.
Okay?
Yep. And notice here, just before Mr. Jackson switches over to the next slide, that for this kind of distribution, if you go far to the left, and imagine that these are little bars. They're so narrow that you can't see them. So imagine that it is a histogram where the interval widths are so small and you're looking at almost an infinite number of vertical bars, that far to the left, you would say that something is less frequent. Right?
Yes.
If you imagine it, that's the height of a bar. And
Yeah.
as you get towards the mean, median, and mode, then you notice that the frequency of that value occurring is the highest.
Yeah.
And then, so what it says is that in nature, some walruses may weigh so little, right, and others
Yeah.
may weigh so much, but that the usual weight is going to be
Yeah.
somewhere around this middle
Somewhere around the
region,
middle.
right,
Yeah.
where most of the data points lie.
Yeah.
And Mr. Jackson's going to explain a little more about the specifics of that for number 4.
For number 4. So we can look at the normal distribution and how it fits in with our standard deviation. Basically, every normal distribution has its own mean and standard deviation, right? So depending on what we're talking about, we'll be able to calculate a mean for a certain standard deviation. For a certain distribution, we'll be able to calculate the standard deviation for that distribution. We've done these things. For every and any normal distribution, this is what is true. If what you have approximates a normal distribution, then 68% of the data, or 68% of the frequency, or 68% of the people surveyed will lie within one standard deviation of the mean. So it means that this area in here, in dark gray, as you can see, represents 68% of the people that were surveyed to get this distribution. Or 68% of the walruses in the world will have this mass in between one standard deviation of the mean. 95% of the data will lie within 2 standard deviations of the mean. So in this dark gray and the light gray, 95% of all walruses have a mass that is plus or minus, the mean plus or minus 2 standard deviations. And then way out here, we've got 3 standard deviations of the mean. 99.7% of data will lie within 3 standard deviations. So that's from this bar and inwards to this bar and inwards. And what you'll notice, what's left over, what's outside of 3 standard deviations of the mean? 0.3%, which is represented by this little tiny bit right here and this little tiny bit right here. Okay, so a tiny, this will give us a really good way, just like quartiles helped us to group things and to say, okay, and percentiles helped us to group things. This really helps us to group things, to see that, holy cow, this walrus is a mammoth. He's beyond 3 standard deviations of the mean. We're talking, the probability of finding a walrus that's this big is really tiny. Yeah. Really, really tiny.
All right, so now, what if we take our normal distribution and we set our mean along the middle, and then we add and subtract +1, -1, +2, -2, all of our standard deviations. Then what we can create is a normal curve where we've got our mean and we've added and subtracted 1 standard deviation as we go down the line. The number of standard deviations that any data value is from the mean is called its standard score, or z-score we use.
Mm-hmm.
So for any data values that would fall below the mean, their z-scores would be negative. And for any data values that fall above the mean, their z-scores will be positive. So what we can do is we can say, all right, if we've got a sample with a mean of 1,010, then I can put that mean along that middle line there. And then I can say, okay, if the standard deviation is 20, if I add 20, I get 1,030, and I add 20 again, and I add 20 again. And so what I've set up for myself are some parameters where I can see where would some values fall. Like would a value of 1,000 fall within plus or minus standard deviations of the mean? And we can see that it would fall within -1. Now what we can do is we can take this normal distribution with our unique mean and our unique standard deviation, and we can standardize it. And what that means is we can superimpose the z-score or the standard score. And remember, a standard score just says, for that value, how far away is that from the mean?
From the
in terms of standard deviations. Okay?
So it basically strips anything here, like any specificity, and units and stuff like that, and it would strip it away so that now we're just talking, okay, how far away is it from the mean?
From the mean. Yeah.
How far is it away, from the first standard deviation? Like, where does it lie along here?
Yep.
And the z-score will actually give you a value somewhere within this range.
Within this range. So if we look at our value of 1,030, and because we added one standard deviation to our mean to get it, it corresponds to a position of +1 as a z-score or a standard score. Remember, the standard score is just how many standard deviations is it away from the mean. So it can be above the mean, it can be below the mean. We can set it up like this so that it's in perfect, like we add exactly 20 and then exactly 20 again. But it's not always going to work that way. There may be some situations where we want to know what would be the standard score for a value that isn't exactly 1 or 2 or 3 standard deviations, somewhere that's on the line that's in between those standard deviations.
So
and we need a formula.
If I had like a point right here or something like that, and I want to find out where that lies, then it's not going to be quite as easy as just saying, oh, so we need to be specific. And how do we get specific? Z-scores.
Z-scores. So for a population, what you're finding the z-score or the standard score, or how many standard deviations you are away from the mean. You take your value of interest, the value that you're standardizing, which is your x. You subtract it from the mean. So essentially you're finding its value away from the mean in the same units that you used for your study. And then you divide by the standard deviation. So if you want to know how many standard deviations you are away from the mean, you take your distance from the mean and divide by your standard deviation. For a sample, it's the same principle. It's just that instead of mu, we use x bar, and instead of sigma, we use s.
Yes.
And this z-score, this value that you get out, is going to be plus or minus or 0, and it's going to tell you, again, how far your value of interest, your x value, is away from the mean in standard deviations. How many standard deviations are we away from the mean? Okay.
Okay. Continuing on then, Ms. Hughes, here's an example that we have where we're going to get a chance to practice this stuff. So you can start us off on this one.
Okay, so let's say a survey of daily travel time was found to be normally distributed. So this means some tests were done on the data and that it is approximating a normal distribution. So we'll tell you that in terms of a test or a quiz or an assignment. We'll say this is normally distributed, so you know what to do. The mean travel time is 38.8 minutes. And the standard deviation is 11.4 minutes. So if we want to take a standard curve or a normal curve and label the normal distribution for 2 sets of values, the survey scores and the standard scores, well, the standard scores are going to be 0, plus and minus 1, plus and minus 2, plus and minus 3. So we can set those along our normal curve, and those are the standard scores. What we can do now is underneath that, we can add in our survey scores. So the 0 means no standard deviations away from the mean, which is the mean. And we know our mean is 38.8 minutes.
So, okay, so we can take this 38.8 and we can just put it right here.
Yep. So a standard score of 0 or a z-score of 0 corresponds to the mean. So it is our mean.
Okay.
Now, if I want to find out what would be the survey score that correlates to +1 z-score, +1 standard deviation above the mean, then I simply take the 38.8 and I'll add the 11.4. So when we do that, we get 50.2.
Okay.
From this point, I'm just going to add another standard deviation. and then I'll just add another standard deviation. Okay, so what we're doing is we're taking the standard scores, which are the first ones, the 0s, 1s, 2s, and 3s, and we're correlating them to what the survey scores would be. We can also go backwards. Again, we take our 38.8, and now we're going to subtract a standard deviation. So 27.4 is one standard deviation below the mean. We can subtract another standard deviation, so that 16.0 is negative 2 standard deviations, so 2 below the mean. And value of 4.6 is 3 standard deviations below the mean. So you just add and subtract your standard deviation, and then you create a survey score that matches your standard scores or your Z scores for the curve.
So with this intact then, let's actually look at a couple calculations of Z scores. So let's find the standardized Z score for a value of 26 minutes, 33 minutes, and 65 minutes to find out how many standard deviations each one is from the mean. Then we're going to mark these points on the normal distribution that we created. So really what we want to do is, let's say we've got these 3 data points, 26, 33, 65. These are waiting times that people have waited. And we want to find out, are these common or are these uncommon? Or like, where do they fit in this whole scheme of things? So to do that, you know, we could look at our normal distribution right now, but it's more effective to find the Z scores. So we know that X bar, this is a sample, so for X bar, we've got 38.8. Our standard deviation is 11.4. So to calculate for 26 minutes, our individual value is 26. And so Z26 then is 26 minus 38.8, all divided by 11.4. And when we work this out, we get minus 1.12.
And this is just using your Z score formula for the sample, where the X value is the value that you're standardizing, minus the mean, which is 38.8, over the standard deviation, which is 11.4. So it's the value you want to standardize minus the mean over the standard deviation. And we just do Z sub 26 so that we can keep track if we're finding multiple Z scores.
Which we are.
Yeah.
So here we have 33 minutes is our second Z score we want to find. So this one we'll label as Z33. Okay? And Z33 then is 33 minus the mean divided by the standard deviation. And when we do this calculation, we get negative 0.51. I'm going to suggest at this point that to find Z65, right, which is X being 65 minutes, that at this point, press pause on the video and try this one for yourself. And so what you should find now that you've done your calculation is you should find that, okay, 65 minus 38.8 divided by 11.4, you should have had 2.30. So our last step, now that we have these Z scores, and this is where we're really going to hammer home the difference in those two labelings on the axes, let's take a look at how we might label this. So let's go back to this diagram again, and we'll say, okay, well, Z26, it corresponded to a waiting time of 26 minutes, which if we're using this lower scale would probably be somewhere in between 16 and 27.4. But this isn't a very nice scale. 1.12, however, is a really nice scale. And so we can indicate that, oh, this right here is going to fall at this location. Whereas using 26, when I have 27.4 and 16.0, that's tough. That's a tough scale to handle.
And even just knowing that it's 26 minutes is not as useful as knowing that it's 1.12 standard deviations below the mean.
Yes.
And then you know, oh, it's not unusual, it's not outside 3, you know, it's close to the mean, so it's a usual value that you would expect to find, right?
So then for a Z score of negative 0.51, this is corresponding to 33 minutes, we would find ourselves right around in this location here. And of course we can label this with a dot on here. And this is within one standard deviation of the mean. So this is actually quite a very common time. And then finally, the one that you calculated for yourself, a 65-minute wait, which is about 2.30, a Z score of 2.30, that's actually going to fall somewhere out here, which is outside of 2 standard deviations of the mean. So now we're starting to say, oh yeah, this is starting to get a little bit less common. So waiting for 65 minutes is more than 2 standard deviations from the mean. And so we would say, yeah, that's a lot less common.
Yeah.
Okay, so let's press on then.
All right, so now imagine if we have one commuter reported traveling 83 minutes to work, and that seems pretty high. That seems pretty high compared to our mean of 38.8, but what we wonder to ourselves, we wonder, I wonder if this might be an outlier. And generally accepted, not always 100%, you might do more complicated calculations when you get in university and you pursue stats, but generally accepted is that values that are larger than 3 standard deviations from the mean are likely to be outliers. Not 100%, but they're definitely going to be flagged and identified as possible outliers. So what we want to do is we want to identify, does this traveler's time represent a possible outlier for this data? Now, we can see that 83 minutes to work. If we look at our right-hand end of our probability or our normal distribution curve, we saw that a +3 on the standard deviations corresponded to a 73-minute commute. So we can see right away that 83 minutes is beyond the 3 standard deviations, which makes it a possible outlier. But we might as well perform the calculations and find out exactly how far away it is using the z-scores. So we know that our value of interest that we're looking to standardize is 83 minutes. We've got our mean of 38.8 and our standard deviation of 11.4. So then we're just going to find z sub 83, which is 83 minus 38.8 over 11.4, and it comes out to be a value of 3.88. So that is way out. That's way away from the 3 standard deviations.
Yeah, this is approaching 4 standard deviations from the mean. So Z sub 83 is really pretty far out there.
Yeah. So we can conclude, not for sure, but this value could be a possible outlier for this sample. And that's all we'll ask you to do in your test assignments and projects, is to identify possible outliers that would have to be dealt with or managed.
Next lesson, we're going to delve more into probability.
Looking forward to it.